So for today, I'm going to talk about how we can control road traffic using automated platoons. We have been working on automated platoons, as Samita mentioned, for quite some time now. I will give a little bit an introduction in the beginning of my talk to the background on this technology that we have been developing. And then the second part, or the core part, will more be on how we deal with a specific control problem, which actually relate to quite a few other talks during this workshop and also previous talks here at the IPAM. So really what this is about, I want to highlight that some of this goes back 10, 15 years. Many students and so on have been involved. The core of what I'm talking about today is work by Matthew Barrow, who actually also giving a lightning presentation, poster presentation later today, and Mladen Cicic. But it's also joint work with many others, and we have been working also with Amin, Yin, and Antonella Ferrara actually mentioned some of the work last workshop here. The starting point of what we have been doing with automating Platoon is basically asking ourselves, how can we make transportation of goods over highway networks more efficient? So this is really a problem of transportation, which is of great importance to society, right? A lot of the transport in the US and all over the world is going on roads and going with this long haulage truck. We're talking about typically millions over a continent. And it's a system today which doesn't have much automation. And the question we're asking ourselves is, could we actually make this system more efficient? Could we automate it and make it more efficient? And the reason for this, you can motivate it for many different reasons. From societal viewpoint, less pollution and so on, but you can also look at simply from an economic viewpoint from a fleet owner. So you see from this pie chart that 1/3 of the cost of operating this vehicle is fuel, another third is the driver's salary. So if you could cut in these two pieces, you could actually benefit from it quite a bit. So this is the general problem we are interested in. And let me illustrate with a movie now how the system we have been developing works like. So we have two different transportation missions going across Germany in this case. These two trucks are sharing a road in time and space there in the middle. If they now share that, they could actually go together in a road train. They could travel together as this while they are traveling over that road segment. So if you now know the source and destination of transportation missions now, right, we could coordinate that so that there is as much of this type of platooning as possible. And here you see the system we have been developing together with Scania, Swedish truck manufacturing. So here you see how automatically the distance between these trucks are being regulated. They are using communication between the vehicle and then an automated control system that makes sure that the distance is kept constant. There are drivers in the seats here, but they are not regulating really the distance that we are here. Of course, just going in steady state there is not so interesting. You would really like to be able to form platoon, as you saw here in the video, and you would like to be able to handle also traffic and so on. So there might be a car that is on the highway entering here into the platoon, and then the system automatically detects that car, gives some space for that car, and then maybe the human driver in that car decide after some time to leave that space, and then the system automatically is then reducing the distance between the vehicles again. So you see there are many things here while we are operating such system in practice that one would need to take care about. And of course, above all, this system needs to be more safe than existing systems. So if something happens in front of the first vehicle, all of the vehicles have to stop instantaneously here. So this is a system that we have been working on. And what you see is a vision here, which you can say illustrated by this cartoon. So we think about in the future, we will still have highways, we will have harbors, we will have factories and cities, and there will be road transportation vehicles or trucks that is transporting across here. But we now form these trains automatically while they are out on the highway. So how should such a system look like? So basically, if one boils it down to engineering such system, one typically come up with some sort of structure, some sort of control architecture that probably looks something like this. So you see here on the lowest level, we assume that we have this capability that you saw in the video, so that trucks are able to go in platoon and regulate automatically the distance between them. One level up, we have a platoon manager, so another system which is able actually to make platoon merge and dissolve and so on. On top of that, we have a platoon coordinator. The platoon coordinator now makes sure that we do as much platooning as possible, so vehicle have some sort of support of the decision they are making, if they should take a certain route or not, if they should depart from a parking lot at some point or not. And then on top, we have the interaction with the logistics system, so the fleet management system that the fleet owner have in the back office, and that these different fleet owners could interact now on a market on different levels here in a systematic way. So this type of architecture we proposed a few years back now. So if you're interested in just reading in general about it, it's in a Proceedings IEEE paper there. But since a couple of years now, we are also working on a quite substantial project called Ensemble, where all 6 truck manufacturers in Europe are more or less implementing this architecture now. So the focus of the project is really on the different level here, including demonstrating Platoon with multiple brand of vehicle there. So in the talk now, as I said, I will talk a little bit first about the lower layers, and then I will come into more the influence this type of platooning, and if we have quite massive platooning in the future, what it has, the influence it has on road traffic. But let's just, for those of you who are new to this, let me just mention a little bit of why we do that. What is the physics behind it? It's very simple. So if you have 2 tracks that travel at some distance, as you see here in the lower plot, there will be a significant air pressure on both these vehicles, and that influence what fuel that a vehicle will consume. If the second vehicle in this 2-vehicle platoon is moving closer to the first vehicle, you see that the air pressure is being reduced. In this plot, you have the air drag reduction on the y-axis and the distance between the vehicle in the platoon on the x-axis. And you see here that the second and third vehicle in this platoon, if they go on a distance like 10 meters behind the other vehicle, there is an air drag reduction of 40–50%. So quite a significant air drag reduction if you travel close. So that type of benefit now also can be extended into the fuel reduction. And now there are other things that come into play, but the fuel reduction you could think about here in our experiment is typically something around 10%. Of course, it depends on the road you drive on and the traffic situation and so on, but 10% fuel reduction on a system that runs 24/7, as typically these modern trucks do in the Western world today, is a significant reduction. So therefore, the great interest for truck manufacturer and others to investigate this type of technology. We and many others have been working on how the actual control is being done on the low level. Here, I won't go into detail on that. I will move up the layers here, but let me just, in a couple of slides, just indicate a little bit how it works. You see that it's actually not very complicated. So this is the architecture inside a single truck. So inside a single truck, you have the information coming in from the left. You have the control computations here in the middle, and you have the actuations to the left. the reference velocity of the truck, if it needs to brake or not, or if it needs to change gear or not. So you see that everything I talk about here, when we talk about doing new control of individual vehicles so they can stay in a platoon, just means that we have changed a piece of code inside the control system, basically the same type of code which is doing a cruise controller in a car or so. So you see that you can say more or less that a driver, or if there is an operator also in the future, could be in charge, basically in saying if we should go in a platooning mode or not. If we are in a platoon mode, we need some certification of the information available and so on. But then it's just a matter of running a particular type of control algorithm here, which is often called CACC, a collaborative adaptive cruise controller in these vehicles we are talking about. So how is that CACC working? Yeah, when it goes in a platoon, it's simply so that this vehicle exchange information. They exchange information in two ways. They have sensors. A modern truck today typically have a radar in front. It has also cameras in front. So it takes sensor information about the distance to the vehicle ahead. And then it also gets information through a wireless communication, vehicle to vehicle or vehicle to infrastructure to vehicle communication about what the vehicle ahead is doing. And with that information, the vehicles are now able to regulate the distance. So that distance, for someone in control theory, you couldn't go to a conference the last 50 years almost without having some papers on this, right? Because it's a nice, it's sometimes called string, to regulate the string here. So it's a nice problem, try to understand how should we, if we have a string of vehicle, how should we regulate the distance between these vehicles? It's typically so that you don't want the control algorithm to depend on the size of the system, so the number of vehicles, and also for other reasons, you would like to use local information of this. And it's been shown by many authors that if you're not careful here, a small perturbation in this system could actually amplify as we move down the string. So you can get what is called string instability. So a small perturbation by the first vehicle here could increase the perturbation of the later vehicle. And that oscillation could then mean that the later vehicle could crash into the vehicle ahead of it. And this has been studied, as I said, by many authors here. I won't go into detail. I would like to show just some experimental work that we were doing on this, just to show you one small little point. So here we are on a highway just west of Stockholm, 45-kilometer highway going back and forth with these three test vehicles. So they are going in a platoon and we are regulating the distance between them. The control architecture here is a standard one for distributed control. So you see it down to the left here in this figure. So you see that each vehicle have a controller, I call it the vehicle controller, that regulates now, the second vehicle regulates the distance to the first vehicle, get information from the first vehicle, how, what the state is now of the first vehicle, its position and velocity, and then it uses that in order to adjust the distance. If we do like that, this is just one short segment of the experiment that we did. We went out several weeks going back and forth. This is just one segment, a few kilometers, a few miles if you want, over this highway. So on the top plot here, you see that we are going, this is altitude. So we're going uphill, then downhill, then uphill, then downhill. The second plot shows the velocity of the vehicles. So the first vehicle in the platoon, the blue one, when it goes downhill here, the speed increases. Then it ends here and goes uphill, and then the speed goes down and so on, right? So the blue makes a quite natural type of evolution there, right? If we now look at what the second vehicle is doing, you see that the second vehicle keeps the same velocity here in the beginning, but then you see that something strange starts to happen. So the velocity of the second vehicle starts to oscillate. So you see, for instance, in the second downhill here, the velocity of the second vehicle oscillates, which means that the distance between the second vehicle and the first vehicle is also oscillating. So it's probably quite scary for the driver now who sits in the second vehicle, because that vehicle is going closer to the vehicle in front, then it's going some distance and so on. And not only that, you see that the torque generated by the engine of the second vehicle is also oscillating. And moreover, the second vehicle actually have to brake a few times in order to avoid running into the vehicle ahead. We wanted to save fuel here, save energy. If we are braking, we are wasting energy, right? We are burning energy. So this is, so to say, the worst thing that can happen here. So what we worked on a few years back was to understand this. So why did this happen? And why wasn't there anything in the literature about this phenomena? So we first thought, of course, that we did something wrong in the experiment and that there was some problem here, but we studied very carefully. And then we start thinking about, could it be something which is challenging with this type of control architecture here? Because notice that we have a particular type of control system here, right? We have a control system where changes in the road topology and changes ahead of us in this platoon will affect us, but will also affect the vehicle behind us. And we are not really, with this architecture, necessarily able to predict very well which will happen far away, even if the vehicle ahead of us, or thanks to the road topography, we could have an idea about that variation. So if you think about that problem like that, you can actually think about that maybe it's clever to regulate, not trying to regulate the distance between vehicles. You could think about instead that you should try to regulate the time gap, delta t, between the vehicles. So you should say that the position of vehicle I and the position of vehicle I minus 1 should be a time delta t between each other. That corresponds to that they should have the same velocity as measured at a certain instance in space. So when they pass a certain point along the road, they should have the same velocity. Of course, at a certain time, they will be at two different points on the road, but when the second vehicle come up to where the first had been, it should have that velocity. This is what the time gap policy would suggest if you do it like this. So this means, from a control viewpoint, something interesting. It suggests that we should use a cascade control. We should not try to actually regulate it just as one shot, as on one variable. We should separate it. We should say that the velocity should be the same for every vehicle, and it should follow a reference velocity in this sense. The second thing is then keeping that time gap. So if we draw a block diagram, it means that we would like to have something which looks like this. So this thing it's not just so to say intuition here. There is we have written some paper about this also. So if you want to know, so to say, the mathematical background or so, one can prove also that this is actually give nice stability result. I decided today not to talk about them here, but talk about other stuff. But if you're interested in them, I'm more than happy to share this information. I would like to show instead that if you now translate what I just showed you, if you translate them into a control architecture, you end up with something like what you see here bottom left instead. So we still have vehicle controllers on the bottom level, but we have then made a couple of extensions. We say now that we have information about the road grade. So we assume that there is a road database that could provide us with the road grade. So we know how the road is changing as we travel, right? And then we introduce a new block here. I call it a Platoon coordinator. So the Platoon coordinator now computes that reference velocity. Remember that each vehicle should have the same reference velocity at the same point in space. So they get the same information from the Platoon coordinator, and then they implement that. So if you do that, so if you run that in the system, Now the velocity is going to change over space here, but all the vehicle under perfect circumstances should keep the same velocity. And this is what you see here, right? Now, if you look at the distance between two vehicles, they will not be constant over time because they necessarily need to change that. And this is what you see in this plot, in the third plot here, right? So they are varying over time, and we need to monitor that it's always along the safety distance that we would like to have. So this is the strategy that we develop. But when we thought about this now, it opens up also some interesting thing, because actually the reference velocity here, that doesn't have to be computed as often as the control command that we do within the vehicle, which is regulating instantaneously if a vehicle needs to brake or accelerate and so on. So the platoon coordinator now could be done somewhere else than necessarily in one of the vehicles of the platoon. So this is something we got a bit interested in now, that thinking about how to control platoon of vehicles from the infrastructure that we have. And
Kalle, we have a question from Benny. Sorry to interrupt. So he'd like to know whether it's the first vehicle. So is what the first vehicle does what a human driver decides, or is it close to fuel optimal velocity profile?
So what happens, that's the good question. So basically in the system we are deploying, there is always a human in the first vehicle that is so to say, doing what a regular driver would be doing if they would be going on their own. But what happens in practice is that those trucks today are already fairly automated. So what is typical, if one study how the driver drives on the highway, you anyhow run a cruise controller. So typically the first vehicle is keeping not constant velocity, but what you do is that you keep a velocity which is now good for the whole platoon. So you can compute optimal reference velocity also there now, taking into account all the vehicles, and then you would implement that in the cruise controller of the first vehicle. But it's not a big difference if it would be so that we don't want to compute that optimally, but instead there is a driver in the first vehicle, and that driver decides how to drive. And we have actually been investigating that problem a bit, because from an implementation viewpoint, what is interesting here from the track manufacturing is how much of this automation is needed in order to benefit. Do we need to actually have full communication between the vehicle, or could we do almost as good as actually having some drivers in some of the vehicle actually doing the command? So there are many different alternatives one can think about there. Okay, thank you. So back on this, so we are not in the individual vehicle now on the controller, but we're saying, okay, we can actually compute the reference for the platoon now, actually outside the platoon. We can think about what is a good reference for the platoon. And why we got interested in that is not only that it's interesting from a traffic viewpoint, but it's actually quite fundamental when we see how communication and cellular technology is moving now. Because basically, as you move now across the road infrastructure, with the cellular infrastructure there, you can think about that you start doing the computations regulating the platoon in that infrastructure. So basically in the base stations. So this is something we are investigating now with the new 5G test beds, and I think it's being deployed now in many places in the world. So basically closing the loop here over the cellular infrastructure, and also utilizing some of the possibilities that we would have with the 5G test there. And one can then investigate, should one do this over the cellular infrastructure or through vehicle to vehicle and so on. But let's leave that a little bit and let's moving up now. So now I'm interested in not regulating an individual platoon, I'm interested in forming a platoon. And in the formation of the platoon, it's simply so, as you saw in the movie in the beginning, that vehicles come from different sources. They could meet potentially at that merge point, and then the platoon for some time before they split. So this basically become a problem now where you are closing the loop over the infrastructure. And the output, the control command, is now suggested speed profiles for the two platoon, like in this picture, right? The one vehicle platoon and the free vehicle platoon, so that they merge smoothly. So basically now, based on the information about the vehicles and the traffic, you compute this type of reference signals there. So these ideas, when we come up with them, we started to do some more experiments. So we are back now here in Stockholm, south of Stockholm, a highway where we went back and forth just 10 kilometers or so, over and over again. And we were interested in understanding how easy is it to actually do this merging maneuver just with two vehicles. So what you see here in the video is that we are merging with a truck ahead of us. And we are doing that over and over again. And we would like to understand, how does the traffic conditions influence the possibility now of doing this merging in an optimal way? And as you see, as we're going down the road here, we are passing these gates where we are measuring the density and the flow through this highway. So we are integrating that information, and out of this information, of course, we can get the fundamental diagram if you want, and we can study this information and see how well we are able to solve this. So let's just look at how one would do that as an optimal control problem here. So what I showed you was basically that we were in a catch-up phase there. After the catch-up phase, we will be in a platooning phase, hopefully for quite some time, when this vehicle would platoon, and then we would split again after some time. So with an optimal control problem, what I mean here is that we can now find the optimal reference velocity for these two different phases, so that we have as low total fuel consumption as possible, given now the dynamics of this vehicle, but also given the traffic dynamics. So think about that this becomes now an integration of the dynamics of the ODE, if you want, of the individual vehicle here, but then integrated in the LWR model. So we try to solve this problem, so it becomes something like this, right? So the upper part here seems fairly straightforward. We just write out basically what would be the fuel consumption under some simplification. But then the challenge is, of course, with the traffic model that we have. But we solve that, and I will just show you here some numerical results. So forget about the color coding here to start with. So you see, if you look at the black dashed line here, you see there is one truck that's starting after 40 kilometers here, starts at this point, and there is another one who starts at 0 here. And then we follow these two trucks. If there is no traffic, they should just keep constant velocity. That would be the best thing they can do, right? If they want to save fuel, and then they will merge at this point. If we now add traffic, so the color coding here is traffic density. The lighter the color, the more traffic there are. And if we now run this system instead, thanks to the traffic, the two trucks will be delayed, and the merge point would be later. And then we will merge instead at the red cross over there. If we solve the problem on the previous slide, what happens is now that we get a different solution. It's optimal to actually merge slower, and you see that the green dash lines is not equivalent to the previous one, and you have a fuel optimal merge point over there. You see also something interesting, which we will talk more about now, is of course that these two trucks, they are acting as a moving bottleneck in the traffic. So you have a built up of some congestion behind these two tracks. And this is a phenomena that we are going to investigate a little bit more here. But of course, with this type of platooning, we are saving quite significant amount of energy. And in this plot, I just show the extra energy we are saving by actually doing this in an optimal way, and how it depends on how much traffic that we have in this situation. So let's now move to another aspect. So if we now imagine in the future that we have quite a few of these platoons around, like the one you see that traveled the bridge in over Stora Belt in Denmark here, so then we can ask, of course, could we now control these tracks in a way which is beneficial for traffic? So we utilize here this bottleneck idea that has been developed also by some other people in the workshop here. So we think about this as the tracks are acting as blocking some of the cars here, and by doing that they are delaying the cars until they come into the congested area in the picture that you see here. So this, we have been studying this phenomena now over the last couple of years with different types of models. With the D'Aganzo's cell transmission model that I just showed you, we have also developed some queuing model for this, and we have also doing some models with front tracking, front propagation models directly from the PDE. Here I will just give you some flavor of the type of results that we have come up to. So let's look at the stop and go wave dissipation. So the control system that I talked about here, it basically have this structure, right? So the color that you see here is the density in this segment along the highway that you saw that we are measuring here on the highway outside Stockholm, right? And the information about that density is sent back to a controller. That controller is now suggesting the velocity reference for this track platoon over there. If we have some traffic jam over at this yellow area, which indicate that there is high density here, potentially we could change the velocity of this track platoon so that it actually slow down the traffic that is entering into that traffic jam. So what would that look like in practice? So here you have a similar plot as before. So you see that we have a traffic jam that is built up here after 40 kilometers. Maybe there is an accident there, and the traffic congestion is propagating backwards in space and forward in time over here. Then we run our track platoon. The track platoon is moving a little bit slower than the car traffic, as you see here. And then when it comes to the congested area, it slows down even more. And then on the other side, it continues like that. What we now can do is that if we have full information available of the state here, we can compute based on a model now of the traffic, how can we now make sure that the platoon meet exactly at the point when the congestion is dissolving over there. And then we can regulate the platoon so that we target that. And this is what you see here. And you see also that we are now building up some congestion behind ourselves by that. So this is kind of the basic idea that we do. Then we can ask a couple of questions. Is this good for the truck if this happens? Is this good for society? Is this good for the rest of the traffic? Or are we delaying overall the traffic here? And the answer is that it's actually good for everybody. So if we look here in another, it's from another paper, but it's a similar spirit here. So in this case, if we just don't apply this type of mechanism that I described, in this case, thanks to the traffic congestion that we have over to the right here, the total travel time of all the vehicles that are traveling through this region, this 5 kilometer, they have a 38% increase in their total travel time due to this congested area. if we now for this system apply that strategy that I just showed you, so we have in this case a number of platoons that we are integrating here, and you see basically how they are acting. And by then doing this slow down in this kind of systematic way, as I described, in this case, the total travel time increase is down to 8% again for all the vehicle, and there is no heavy area of congestion later on. In both these cases now, I showed this under perfect information. So I indicated now what you see here in another setup, that if we have no control, we could have this heavily congested area with perfect state information about the traffic. We actually can improve considerably. But that means that we have perfect information from the vehicle that we have. So what if we don't have perfect information? So for instance, if we imagine that we use vehicles here or the trucks or so as also probing vehicles that gives us sensing information, we can also decide to only use some of the trucks as actuators here in this setting. How does this change the setup? And of course, it changes it. If we don't have perfect information, we need to reconstruct the state information instead, right? And this is what I illustrated here. So you can imagine that if you implement this system, you would at some point, as indicated in this error, with this arrow, you indicate that actually we should start trying to reconstruct the congested area, the state here in the congested area, because some vehicles have detected automatically that there seems to be some congestion. And then based on this information, you could now decide to actually inject more of these probing vehicles. You basically decide to use more vehicle in order to get sufficient information. And out of this information, you can now reconstruct then the state. So this is a difference between these two plots here. To the left, you see the density is a true density in the color coding. The right is now the reconstructed density out of these vehicles that communicate this information. And then out of this information, you can imagine that you now actually dissipate the stop and go wave here by acting on specific vehicles. And then, of course, you can imagine that you have this system now integrated with more and more vehicles as they come, or you decide at some point that this is not needed any longer and you switch off that system. So it's some sort of dynamic way of using vehicles for this type of control. So with that, I think I would like to come to the conclusion. So I described in the beginning this automated road freight transport system that we have developed based on platooning and vehicle-to-vehicle communication and so on. There is a significant benefit of this type of system, and there seems to be some push also from industry in some interest and to test this. And then I talked about that particular interesting problem about controlling the traffic using this type of platoons. And if someone is interested, of course, I'm around. I'm at IPAM, and we'll be more than happy to talk about this. I also, as I said initially, we also have there is a talk by Matthew Barrow here at lunchtime. He have some more details on this reconstruction problem, that we also use some learning-based methods for that. But with that, Samita, if there is time, I'm more than happy to take any questions or have any discussions here. Thank you.